And I want to make sure this is recorded and on the video that I post online so that everybody knows. Again, I ask everybody to chat me your first and last name. That way I can use that as a role of who's here. If you slip out later, I don't really care. It's not a problem. I mean, I hope you don't, unless you have to. I completely understand. But I hope you don't so that you can be here to ask questions. But I want to remind everybody that one, if you don't want your name or face or likeness to be on the internet, you need to send me an email in writing and letting me know that you can't be on the internet that way. And two, you need to also change your. Uh-oh, somebody said they think I'm muted. Anybody else agree that I'm muted? Looks like not. It looks like they did. Maybe something wrong with your particular audio, Zora. Sorry about that. But as I was saying, you not only need to send me an email letting me know that you don't want your face or name to appear on the internet, but you also need to change your Zoom uh, username so that it doesn't appear because your whole name is appearing right now. You can change it, like in my case, it'd be Billy Y or something like that. That'll be fine, or whatever you want to change it to uh, will be fine. And I can always check because I'll see what your username is, and then when you chat me your first and last name, I can make the connection between the two. Caramel did say she heard me, so I think we're doing pretty well. Anybody have any questions before we get started? Sorry, I had to open my mouth and stare a little bit. All of a sudden, a window appeared that I didn't know existed or whatever, so I was trying to figure out what's going on. I'm sure I look really smart going, All right. Well, we're going to go ahead and get started. The last time we spoke, we were going over chapter one. I'm going to continue to try to log people in as they get here, but we were going over chapter one, and I had advised you guys that section 1.1, how science works, section 1.2, models, theories, and laws, section 1.3, measurement and uncertainty, significant figures. I advised you that I wasn't covering that other than what I did last time, which was a little off the cuff explanation of the scientific quote unquote method as I see it in reality play out. So you don't want to answer any online homeworks, online test questions, online practice questions for your practice test, or your actual test that we take. You don't want to answer those based on the answers that I told you. You want to answer those based on the reading that you get in sections 1.1, 1.2, and 1.3. So make sure you read those. I did cover pretty much what the rest of the sections are, which is 1.4 units, standards in the SI system, converting units, order of magnitude, rapid estimating is section 1.6. That's what I'm covering today. And then I did do dimensions and dimensional analysis. I also mentioned unit analysis. The only difference being what I showed you with dimensional analysis, we use capital M for the dimension of mass, we use capital L for the dimension of length, and we use capital T for the dimension of time. But in unit analysis, we would use for mass the kilogram, and we would use for length the meter, the lowercase m, and of course the lowercase kg for kilogram, and we'd use the lowercase s for seconds. So the only difference is using that instead of m, l, and t. So that's the only difference between unit analysis and dimensional analysis. But that is definitely a topic that you need to be able to address. So there will almost certainly on one or multiple tests this semester be a problem where you're going to have to use dimensional analysis. It might be something like I'll tell you, hey, such and such a function gives the energy and the dimensions and units of the energy are blah blah blah, and then I'll say you assume that it depends on these quantities, and these quantities have dimensions and units of blah blah blah. Derive a formula that would be reasonable for this energy formula. So that's a very typical question. You can also see questions like, is it okay to add what this term and this term, given what the units of these terms are, that kind of stuff. So all of those different types of problems of dimensional analysis, you can see some of them at the end of chapter questions where it says the chapter one problems. Specifically look in subsection 1.7. problems, and you'll see some typical examples of what to expect. But also, when you start taking the practice tests, you'll be looking at questions that I usually use specifically for the tests. So, anybody have any questions? A lot more people have come in since I started talking. So I want to give you one more opportunity to ask me questions before we get started. And of course, at the end, you still have, like I always do, as I normally tell you, I'm going to wait here till the last person leaves in case anybody has any questions. So you have that time as well. But make sure you chat me your first and last name if you haven't done so already, and ask me any questions if you have them. Otherwise, I'm going to go ahead and start rolling with the chapter one, section five, or section six, order of magnitude rapid estimating. So it does not appear we have any questions, so I'm going to go ahead and jump right in. So let's start off by sharing my iPad screen. And sharing my iPad screen, that should come up in a minute. I've taken the time because I had a little time when I signed in. I've taken the time to write the question, some of the questions out already, so that'll save us a little bit of time. Really, to be honest with you, we have more than enough time to finish chapter one, and there's a little bit of stuff I could get started on in chapter two, but I'm going to do very little, if any, of that. I might just give you a little rolling history of physics to some extent, so you'll have some idea how all these parts of physics stick together. That's what I did in the last lecture, which was last night. This lecture is more or less a similar version of what I did last night. So if you don't get enough out of this one, or if you need more explanation, look at the video I posted for last night as well. It was posted, I think I posted it last night, but I might have posted it this morning. I can't remember. So you can look at that, and it's on order of magnitude, I think was the title. So you can just look at my YouTube channel and check that out. We're starting off with this example, 1-5, which is very much like the one in the book. This one example, the next one, the purple one, that's very much like the one in the book, but I'm using a specific example. What I want to tell you is that these order of magnitude and rapid estimating questions, they're not only do you know how to calculate and estimate stuff, they're also about do you know how to estimate the sizes of things? Because part of what you're supposed to get from a physics course is a feel for how big a meter is, how big a centimeter is, how big a millimeter is. You're also supposed to get a sense of how big a kilogram is. You're supposed to be able to get a sense of how long a second is. But luckily, the time constraints that we use in the SI system are all the same units that we're used to. They're seconds, minutes, hours. Of course, if you go longer than that and you go, years and stuff like that, that's a little different. But we'll discuss that as well. But one of the things, like I said, you're supposed to be able to look at things like, let's say, look at the room you're in and estimate how wide the wall you're looking at is, and estimate how tall the wall you're looking at is, and then the wall adjacent to that, how tall is that, and how wide is that wall, and then the wall adjacent to that, how tall is that, how wide is that, and then the other one as well, and do all that in meters, not in feet and inches, but in meters. Uh, that being said, if on a test you make an estimate and you do it using feet, that's fine. But if you do the calculations using feet and inches, I'm probably going to take off. So, in other words, you can make the original estimates of sizes in feet and inches, but then you're going to have to convert them to centimeters or meters or millimeters or whatever. So, to give you an idea of what these measurements are, I've told you that a meter is about like 39 and an eighth of an inch, something like that. I normally tell people it's the height of a doorknob. So if you measure up from the floor of your house up to the top of your doorknob, that's roughly a meter. I can tell you that a centimeter is about the width of my pinky nail. So from that skin to the side of my pinky nail, across the pinky nail to that skin on the other side of the pinky nail, that distance on my pinky nail is about 1 centimeter. If you have smaller hands than me, then it might be your ring finger or your index finger or something like that. So that's something you also need to know. You could also say that a staple is roughly a centimeter. The width of a staple, when the staple shaped like it's shaped like this. The width of that's usually around a centimeter, and the thickness of the metal that that staple's made out of is usually close to a millimeter. So that's some of the stuff we can use. I'll also tell you, for instance, here I have one of those vanilla gift cards. And I'll tell you that a credit card, a debit card, or a vanilla gift card, that sort of thing, the thickness of that is right at a millimeter. I even just double checked to make sure because I was pretty confident it's pretty close. And yeah, that is just a moderate amount smaller than a millimeter. I'd say this is probably about zero point 0.9 millimeters for the thickness of it. So hopefully you can use that information to sort of picture things in sizes of meters and centimeters and millimeters rather than feet and inches. Uh, so now that I've discussed that, we're going to go ahead and start doing the rapid estimating or order of operation, or excuse me, order of magnitude calculations. I'm going to give you some caveats on that. For instance, when you do the homeworks, they have some order of magnitude calculations you're supposed to do. Like I think one of them was related to the Pentagon and stuff like that. One thing that I've noticed students make a mistake on when they're doing that is they often don't realize that in most of those problems, the online homework system is asking you for the order of magnitude. And what they mean by that is they're asking you for the exponent that's on the power of 10. So when you do a calculation, you might get, 1 or 2 or 3 times 10 to the eighth, and they ask you for the order of magnitude of the size, then you're going to say, okay, it's 8. So I want to point that out because I know that's a problem that students keep running into every semester and they can't quite figure out what they're doing wrong with their rapid estimating. This rapid estimating, us in physics generally call Fermi calculations, Fermi. That's me saying Fermi in an attempt to try to pronounce it in an Italian way because Enrico Fermi was a Italian physicist and he was brilliant. In fact, I have one of his biographies. It's called The Last Man Who Knew Everything, and he's sort of one of those Jeopardy types. Like I suspect he would have been very good on Jeopardy. He knew something about everything, and he expected people that hung around him to, be interested and curious enough to know about those things. So, like one time, he asked his students how many piano tuners there were in Chicago, or it might have been San Francisco. I can't remember, but I know ultimately he ended up at University of Chicago. But this might have been when he was at Caltech or UC Berkeley or one of those places. So it could have been any of them. But what he did was ultimately do a rapid calculation to estimate how many piano tuners, and then one of his students went and looked in the phone book and found that's a thing that we used to have is a book of phone numbers for everybody in the area, and they looked it up, and he was right on the money for the rough order of magnitude for the number of piano tuners. Now, what I say when I say that he was right, what I mean by that is if he came up with 100, then 200 would be acceptable, and 99 would be acceptable, and probably even 90 would be acceptable. So that's an order of magnitude calculation. But he was really, really good at doing it. For instance, he appeared in the Oppenheimer movie. If you remember when they were doing the Trinity test, there was this one guy that dropped some particulate matter like grass clippings and dust and stuff like that, just as the pressure wave was coming from the Trinity nuclear test. And what he watched was those particles go like this. And what he did is he realized that he could estimate the power output of that actual nuclear explosion by seeing how much those particles of grass went back and forth. And upon doing that calculation in his head really rapidly, he already knew the power of that explosion or the energy of that explosion. And then later, once they did the full calculation, they found that again, he was right on the money. So he's really an interesting character. I highly recommend you looking into reading about him. There's some nice biographies of him, of James Clerk Maxwell, of some other people like Dirac was another good a good biography I read. Newton, there's a couple of decent biographies about them as well. And when you read about them, you learn quite a bit of stuff about physics and how they did physics and how they did science and stuff like that. So I highly recommend it. But now that I've given you that background, let's go ahead and start with example 1.5. Estimate how much water by volume there is in a lake which is roughly circular with a diameter of about 1 kilometer. Assume you believe the average depth to be about 10 meters. So this is a key thing that you need to understand. There's probably very few, if any, absolutely circular lakes on planet Earth. There probably are some, to be honest with you. There might be one or two that are literally made in such a way that they're perfectly circular, mainly because craters that form from meteorites and stuff like that often turn out to be circular, at least initially. But either way, the main thing is it's better to use the tools that you know and you can easily do and get as close as you can by further and further approximating it than it is to just assume it's some random shape and start trying to do rough calculations. That's just hard. So if you see something that looks like this roughly and it might have some jagged parts, you're still going to treat that like a circle. So that's what we're going to do here. And in fact, what we're doing is we're assuming the lake is a cylinder because we're assuming that it has an average depth. And by average depth, what we mean is there's some parts that are less deep and there's other parts that are more deep. And by taking this particular average depth, that's going to give us what we think is a rough estimate of the average depth so that when we figure out the volume of a cylinder, then we can use that as a rough approximation of the volume of the actual lake. So right now I'm looking at a cylinder and we said the diameter would be about 1 kilometer, so that means the radius is about 500 meters. And we said the depth, obviously this isn't the scale, but we said the depth we're going to assume is about 10 meters. So that's a very common trick. In fact, if you've ever watched, for instance, Big Bang Theory, one time Sheldon got up to tell a joke, and his joke was assuming spherical chickens or something like that. That is a very real thing. That's why they make jokes about that on Big Bang Theory and other shows, is because it's very reasonable for us to assume a balloon is spherical or a chicken is spherical, or if we want to estimate, this is another problem, for instance, I've done in my own class as well as I've had teachers ask me. They'll say, all right, you're in this classroom right now. You're taking your first test in physics. I want you to estimate the width, height, and depth of this classroom, and then tell me how many dead fruit flies you could fit in the room. So in that case, you might wish to assume the fruit flies are little cylinders, or you might wish they're little rectangles and assume it that way. That's because you can get a rough estimate of how big they are by using those shapes, and you can easily do the mathematics associated with calculating their volumes or areas or lengths or whatever. So that's what we're doing here. So we're going to assume that that is the actual dimensions of our lake, and therefore the volume of the lake is going to be solution V lake is approximately equal to the volume of a cylinder, which equals pi r squared times h. So the volume of this lake is approximately equal to 3.14159. Now, I do that, but really when you're doing order of magnitude calculations, you don't necessarily want to round the numbers early, but you definitely don't want to use six decimal or six sig figs. That's just overkill. But, our calculators are automatically programmed to write pi to like 8 decimal places. So I'm just showing you that. But what you do plan to do is when you're finished with the calculation, you want it to have usually just one significant figure. So only one digit that's not zero. So I'm going to say pi times r squared. We said the radius was about 500 meters. I'll square that. And we said the depth was about 10 meters. So now I can go ahead and do the math here. And I'm going to turn on my calculator first because evidently that really helps. So 3.14159. I actually type it in, so I'm a loser. But anyways, times 500 squared times 10, and this gives me 7.8, which is more, well, really the nature of it is you're initially going to get probably multiple sig figs. I'll call this 7.85 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6, and the units turn out to be cubic meters. So that's the actual estimate, but we want an order of magnitude approximation. So we're going to say V lake is approximately equal to, notice this 7.85, that's almost all the way up to 10, so we might as well call it a 10. So you could call this either 10 to the 6 cubic meters, or you could call it 10 to the seventh cubic meters. Both of those would be acceptable in my class. Okay. When I go to grade something like this on your test, I'm looking to grade your approximation of how big you think the thing you're estimating is. So, for instance, if I ask you a question about the room you're in or something like that, well, it's a little different, of course, for you guys because you are internet. So I can't ask you those kinds of questions, but I have to ask you other things that everybody sort of knows. And if you take the time to write out what your approximations are, then I can give you partial credit. But you also have to do that for these type of calculations because I can't give you any credit at all if I don't know how you got the calculation. So in this case, we're going to say 10 to the 6th or 10 to the 7th cubic meters. In that case, if it was a multiple choice, I would have answer choices like 10 to the 6th, 10 to the 8th, 10 to the 4th, 10 to the negative 2, 10 to the 10th, right? I wouldn't have both 10 to the 6th and 10 to the 7th because both of those I consider fairly approximately the same. Okay. In other words, approximately both are correct. Both are acceptable. Any questions on that particular problem, anyone? I do want to remind you guys when you do your work on the tests that aren't the online tests, the face-to-face ones, you need to show me your work, and you need to start with the equation as it's shown. Start with the equation or the equations plural that you're planning on using to solve the problem. You want to start off writing down each individual number that was given to you or implied by the problem that you're reading, and you want to write that number down with its units and then give it a symbol, ideally one of the symbols that's relevant to our formulas that you have on your equation sheet. Once you have all those, you're going to also write another symbol equals question mark, and that's the thing or multiple things that you're going to write down equals question mark about to indicate what you're trying to solve for. And then you're also going to take an unadulterated version of one of the equations or multiple equations off of the equation sheets exactly how they appear on the equation sheet. So make sure you start off with one, two, three, however many equations you need that are exactly in the form of the equation sheet, and then show me you taking those numbers with their units and plugging them into that equation and then solving it or doing whatever algebra, arithmetic, or calculus you need to do. If you show me all those steps that way, then I can give you copious amounts of partial credit in the event that your answer is wrong. If you don't show me what approximations you're making, for instance, what you estimate the diameter of the lake to be, or what you estimate the depth of the lake to be, or if you don't tell me that since something was dropped, that is understood to mean that the initial velocity was zero. If you don't do those kind of things, then I can't give you any partial credit. And if you have the answer and it's right, but you don't show any work, I can't give you more than probably 50% of credit for the point. I mean, for the problem. So you've always got to show me work unless I explicitly tell you you need not show me work. All right, so let's go on to this other example. The next example says estimate the thickness of the paper used as pages in the books he shows you. I don't know why I wrote he. I think I had started saying estimate the thickness of the paper used in the book your instructor shows you. So that's what I mean here. Estimate the thickness of the paper used as pages in the book your instructor shows you. The book has 750 pages according to the typed page numbers. So I have a book here, Numerical Recipes in C by Saul Tukolsky and other people people. But the main thing I want you to see is the thickness of the stack of paper that makes up the pages. So from this inside or this inside top edge of the back cover to the inside lower edge of the front cover, how thick is that in centimeters or millimeters, not in inches or feet? So it would be nice if y'all could tell me that. Does anybody have an estimate of about how big that stack of papers are? Again, I'll hold them right next to my eyeglasses so you can see roughly how big it is compared to something from everyday life. These are prescription glasses, but they're Oakley's, so you know there's not a huge range of the size of this particular type of frame with Oakley glasses, so you should have a sense of it. Anybody have any idea roughly how many centimeters thick that stack of papers is?
Maybe like 4 centimeters.
That's excellent. That was exactly the approximation that I made as well. I want to teach you about this as well. Larry Weinstein at ODU, I know him. He does. I don't know him that well. I've only met him a couple times, but he's a nice guy. And he wrote a book called Guesstimation, and recently he wrote a newer version called Guesstimation 2.0. And he's really good. He's like this Fermi guy in that he really tries to make rapid approximations to stuff and does really cool calculations. He's even been able to figure out how Enrico Fermi did that calculation of the Trinity test. So it's kind of cool. But he came and gave us a talk one time and taught us some stuff. And one of the things he taught us about when you try to estimate something like the thickness of the stack of paper is maybe you don't know how big it is. I would agree. This does appear to be about 3.5, 4 centimeters to me from the thickness of this white stack of paper. But he says that's not really too bad of an issue if you don't really know. But what you can do is you say, okay, how big do you know it's bigger than? So, for instance, I can look at this and I know for a fact because my pinky nail is the width of a centimeter. So I know it's bigger than 1 centimeter. I can also say I know for a fact it's bigger than 2 centimeters. I can also say that this one's definitely bigger than 3 centimeters. So if you get a number like that that you think is about as big as you can go before you have to say I know it's bigger than before you can stop saying I know it's bigger than that, then you can use that as a lower limit. And then you can say, well, I also know it's definitely less than 10 centimeters because 10 centimeters is, on the order of it's on the order of about 4 inches. So it's certainly not that. But you could probably do better than that. Maybe you can say it's definitely less than 5 centimeters. If you could really make that statement, say it's definitely less than 5 centimeters, then what Larry Weinstein would suggest is you take the 3 centimeters and the 5 centimeters and you calculate the geometric mean of those. The geometric mean is just the product, and then you take the square root of it. So you could take 3 centimeters times 6 centimeters. That would give you 18 centimeters squared. And then you take the square root of that. And of course, the square root of 16 is around 4 point something. So you get, again, roughly the 4 centimeters. He also uses other approximations like the square root of 10 is approximately equal to pi, stuff like that. But that's a good way to do it. You can also just use order of magnitude. Like, yeah, I would really prefer you to go up to as large a number that you can say it's definitely bigger than, and I'd like you to go to a smaller number that you could definitely say it's smaller than, and then do the geometric mean. But you really don't have to be that precise. You can literally just use order of magnitude. So you can say, I know this is bigger than 1 centimeter, and I know it's smaller than 10 centimeters. So a first order approximation would be the geometric mean of 1 and 10. So you'd say 1 centimeter times 10 centimeters gives you 10 centimeters. And the geometric mean, of course, is the square root of that. So that's the square root of 10 centimeters squared. And again, like he said, the square root of 10 is approximately pi. So I'm going to call that 3 centimeters. It's not the 4 that I estimated and that one of your students estimated, but it's still pretty close because we're really just looking for an order of magnitude, not the exact number. So keep that in mind, that geometric mean and those other approximations. I'll give you some other ones later. So uh, I estimate the stack to be 4 centimeters thick. Now, we also said that the number of pages according to the page numbers is 750. Now, there's a little trick part there. Is anybody thinking what I'm going to do here is my idea is I divide the thickness of the stack of paper by the number of pages, and then that will give me the actual thickness of a single page. But there's a danger here. Should I divide that thickness by 750? Anybody have an answer for that? How about, can anybody know why I'm thinking that that's not what you want to do? Does anybody understand the dilemma by saying it's 750? Okay, so this is just some clean thought stuff and thinking about everyday life and remembering, hey, this is stuff I know about. So, for instance, when you look in a book and you open up a page, this page might say 351. So, this is page 351, but then you look on the back of that same piece of paper and it says 352. So we have to divide the number of pages by two because the number of printed pages is actually counting the front and back of each page. So I don't want to divide it by 750. I want to divide it by half of 750, which is about 375. So the thickness of the page is approximately equal to thickness of the stack divided by the number of pieces of paper. And I'm saying number of pieces of paper because the word page means two things. If you take out a single sheet of paper, you might call that a page. But if you take out a single sheet of paper from a book, then that's actually two pages. The front is one page and the back is another page. So that's why I'm trying to use pieces of paper and stuff like that. So in this case, what we're going to do is we're going to say that it's 4 centimeters divided by 375 pages, and therefore the thickness delta T is equal to 4 divided by 375. Oops. And in this case, I get 0.0107. That's what it rounds to roughly. 0.0107 centimeters, which is pretty small. In fact, that is about 0.0107 millimeters, but really this is a order of magnitude estimation, so you're really only supposed to use one sig fig, and that's millimeters. So I'd say delta T is approximately equal to 0. Oops, I made a writing mistake here. I don't know why I did what I did, but I made a writing mistake. It's 0.107 millimeters. So in this case, I'm going to call it zero point 0.1 millimeters. So that's the estimate of the thickness of a single page of paper. Now notice that's way too small. Like if I had a measuring device, it's way too small for me to measure that distance because the millimeters literally at least 10 times thicker than that. And in fact, this is probably a little too thick. But either way, that gives you a rough order of operation. Excuse me, I keep wanting to say order of operations. A quick order of magnitude calculation. Anybody have any questions on that? All right, so we're going to go to the next example, which is example from the book, example 1-7. It says, consider the figure below and use that figure to estimate the height of the building. So this is a drawing like the one in your textbook, and it has a red building over to the right. There's a level ground. There's a person standing on the level ground, and we were nice enough to give you that the height from the ground up to the eyeballs of the person's about 1.5 meters. meters. And what the person does is gets themselves by a sign and then looks up at such an angle that he just skims across the top of the sign and also sees the very top coping of the building. That line of sight you see goes straight out of his eye, right across the top of the sign, and then ends up at the top of the building like that. So that actually forms a right triangle, and that's what we're going to make use of to try to solve for the height of this building H. We're going to start by solving for the height of that right triangle that I have drawn here. This is the right angle, so that's a right triangle. We're going to solve for x, and then once we solve for x, we're going to have to add the 1.5 meters to it because obviously the x starts at the height of the eyeball of the viewer. The other thing we know is that the viewer chose to measure the distance from his eyeball to the sign, and horizontally that distance was 2 meters, and he also chose to measure the height of the sign, and that was 3 meters tall. And finally, he measured the distance from himself to the bottom edge of the building, and that was 18 meters. So what we have here is what's known as a similar triangle situation. So similar triangles, just in case you never had geometry, similar triangles can look like this. You could have, for instance, one continuous line, and they'll do something like that. If they're both right triangles and they're set up like this, these two angles right here are called vertical angles because they're across opposite sides of a vertex. So when you have it like that, that is a good reason to believe that it is in fact a similar triangle. Another way that we list similar triangles is you can have a big triangle like this, and then inside of it is a smaller triangle. So this triangle is in fact a similar triangle with the whole triangle. So that's two common ways to realize that if you have triangles drawn this way, then those two triangles are by necessity similar. And when they're similar, that means the ratios of their corresponding sides are equal. So for instance, if I look at this side divided by this side, that corresponds to this side divided by that side. Or in this case, if I look at this side divided by that side, that corresponds to this side divided by that side. So that's the main trick of using similar triangles in case you haven't had geometry or in case you didn't understand geometry that well. That should help you quite a bit. And we do have to use a lot of it. As I told you, the nasty part about physics is we sort of go on the assumption that not only did you have every class that we expect a college level student to have had to get into college, which means you had pre-algebra, you had all the arithmetic you needed, then you had pre-algebra, then you had algebra 1, then you had algebra 2, then you probably had geometry, and then you had trigonometry, and then maybe even you had pre-calculus, or maybe you just went on straight to calculus. And then once you got to university, you're taking a calculus-based physics where we assume you've already had Calc 1, and we assume not only that you had all those courses, that you perfectly mastered them because we're perfectly free with choosing any topic out of any of those courses and assuming you know it. So even things like long division of polynomials, that was a pretty obscure thing that you did in pre-calc or hopefully in algebra. So that's something we expect as well. So with that in mind, let's go ahead and show you how to work out the similar triangles and use triangulation to figure out what it is. So the solution is as follows. The 2.0 meter by 3.0 meter triangle is similar whoa, nearly, to the 18 meter by X triangle. So what that tells us is, in this case, it's not technically a 3 meter triangle. Let me go ahead and correct that. It is in some sense three, but it's not three because notice that 3 meters goes all the way to the ground, not from the bottom of the blue triangle up to the line of sight, but from the ground up to the line of sight. So it's not even a 3 meter. So let me put an X through that just to make sure you guys know that it's technically a 1.5 meter by 3. So if I compare like sizes or like sides, their ratios, then what I can say is this little triangle right here has 1.5 meters and this triangle also has 2.0 meters, whereas this is 18 meters and this is X. So when we go to use similar triangles, I can do it as follows. I can say 1.5 meters is to 2.0 meters as, remember the 1.5 is the vertical, so that corresponds to the X, and the 2.0 meters is the horizontal, and that corresponds to the 18 meters. So what we have now is X is going to be equal to 1.5 meters over 2.0 meters times 18 meters. 18 divided by 2 is 9, and then 9 times 1.5 is 13.5. So we get 13.5 meters is X. And H, by the way, is equal to X plus 1.5 meters. So we can say that the height of the building is approximately 13.5 meters plus 1.5 meters, which equals 15 meters. So we would call this height 15 meters. So that's another estimate. And there's lots of cool little ways you can do it. A lot of people would just take and walk until they know for a fact that they're looking up at 45-degree angle. It's pretty easy to sort of get a sense of roughly when 45-degree angle is because 45-degree angle is perfectly horizontal to perfectly vertical, which is really a painful way to look up. And then you cut that right in half, and you'd have exactly this a 45-degree angle. But you could also use a protractor. If you just take a protractor and look along the flat side of the protractor with a little weight hanging from the hole in the protractor, that will actually allow you to measure the angle up at which you look. And if you do choose 45-degree angle, then you know that you're looking at a triangle that has a height and a width that are equal. So if you look up at 45 degrees and you know how far the building is from you, then you know the building, at least from eye height up, is exactly the same height as it is far away from you. So if it was 18 meters away, you would conclude that the height of the building would be 18 meters high plus the height of your eyes. So that's another way of doing it. Anybody have any questions on that? All right. Ashton was writing about apologizing for being late. I don't mind you guys at all being late. It's cool. I do the same thing with my lectures. If you don't come in and be, interrupting or anything like that, it's no problem at all. So yeah, by all means, if you're going to be late, I don't have a problem with that. If you have to leave early, I don't have a problem with that either. So we just finished example 1.7, which was estimating the height of a building. Now we're going to go to something a little bit more human. And actually, I think I have enough room for it here. Let's do this one. I'm going to say example, and this example is one. Whoa, well, that was weird. I don't know what happened, but my pen just changed. Oh, I see my pinky leaned over and touched a highlighter. So this is example 1.8. And what it says is estimate the total number of beats a typical human heart makes in a lifetime. So how many beats does a heart have to make on average. And I'm technically talking about a human heart, but I chose not to take the time to write the word human. But hopefully, y'all all get that because it obviously would be a different calculation for another species. So that's the question. How many beats does a heart have to make on average? In other words, during a whole lifetime. So, in order to do this, what I would say is we're going to estimate how many beats per minute because that's a common number that most people know. In fact, most people would say that the heart beats about 60 times a minute, and I rarely find people whose heart beats about 60 times a minute. If they're up and awake, even if they're sitting down, I don't find their heartbeat to be 60 beats per minute. It's normally higher. I have been on medicine before where my heart consistently ticked at about 50 beats per minute, which was kind of nice, but also a little scary because I just thought I might just die or something because I'm a hypochondriac and a weirdo. So, anyways, what I'm going to do is I'm going to suggest that the average human heart beats about 70 times per minute, and I'm also going to say once we know that, I then need to know on average how long a person lives. So this is just sort of common knowledge that people that are adult age are sort of expected to know from a science standpoint. And not only that, some other numbers you sort of should be expected to know. So I'm giving you this as a warning. Those numbers, for instance, like I did in compute and converting 60 miles per hour to meters per second, how many feet are in a mile, how many inches are in a foot, how many centimeters are in 1 inch, that sort of stuff. That stuff I expect you to know. But not only that, what we expect you to know is roughly how many people are on planet Earth and roughly how many people live in America. Those are very typical numbers. You could also, a thing that I've seen instructors assume that their students knew is roughly how many degrees of latitude is the United States wide from California, for instance, to like Maine. So that's another thing you ought to know. I will tell you, by the way, that the number of people on planet Earth is about 8 billion, a little bit more than 8 billion, maybe 8.2, somewhere around there. The average or the number of people in America is around 370 million right now. I would say that's a pretty good approximation, stuff like that. So just keep that in mind. So in this case, we're going to take the number of beats per minute and then we're going to figure out how many minutes there are in the average human lifetime. And I'm going on the assumption that the average human lifetime is about 75 years. If you look it up for America, you'll find that we're right around 70, 73, something like that. Women live a little longer than men, so it might be more like women live 74 years and men live like 70 years or something like that. And some other countries have, 80 as their average life expectancy. I think I learned that it was either Italy or Greece the other day. I found that their average life expectancy was like 79. So that's something that happens. So what I'm going to do is start off with the idea of 75 years. So, solution. Actually, no, I'm going to start off with the idea of 70 beats per minute. So 70 beats divided by 1 minute. Okay. Now I have the number of beats per minute. If I convert that to beats per lifetime, then I'll have the answer. So I need to convert from minutes to lifetime. So how do we do that? Well, what I know is that 1 minute is equal to, of course, well, actually, I don't want to do 1 minute. I'll say 1 minute. No, I'll say I'm going to go bigger from minutes to bigger and bigger units. So I'm going to say there is 60 minutes in 1 hour. So 60 minutes equals 1 hour. And you can see by doing that, I have canceled out the minutes and I now have beats per hour. But now I got to keep going because I got to get up to a lifetime. And what I know is that there are 24 hours in one day. So now I can say that the hour canceled out with the hour over here, and now I've got the number of beats per day. Then I got to remember, well, how many days are there in a year? This is another fact you should know. So I'm going to say there are roughly 365. Oops. And I'm going to do a little dyslexic thing there. 365.25 days in 1 year. So now I have the number of beats per year. And now all I have to do is multiply by the number of years in a lifetime. And notice how I'm thinking about these units, and they actually tell me how to write the fractions as well as how to do the multiplications. So in this case, I'm now going to say that there are 75 years in one life on average. So, like I told you before, when you do a long string of conversions like this, you multiply all the numerators to get a new numerator, then you multiply all the denominators to get a new denominator, and then you divide the numerator by the new numerator by the new denominator and write the units on it, and that's what your answer is. So, in this case, I notice how I wrote sort of like a dagger going down and to the left. So I used a separate symbol for each thing. And now you can see I have beats per life. And the answer for beats per life is, notice all the denominators are one. So I don't have to do anything with that. I'm just going to take 70 times 60 times 24 times 365.25. I sometimes will call that 0.24 because if you haven't noticed, there's not a solid rule that we use for leap year. It's not exactly every fourth year we have a leap year. We have a every fourth year we have a leap year unless that year is a multiple of four. And then we have another rule that if that year is a multiple of four, but it's also a multiple of 100, then we do have a leap year. So that's all numbers that we've used, are methods that we've used to correct for the fact that the year is not exactly 365 days, not exactly 365.25 days either. Okay, so that's what I'm doing. I've got 70 times 60 times 24 times 365.25 times 75 years, and that gives me, I'll write it in scientific notation. It's 2.7. Actually, I should call that 2.8. So it's 2.8 times 10 to the ninth beats. So the number of heartbeats is around 2 times 10 to the ninth beats. Anybody have any questions on that one?
Is it close enough to three that you could say 3.0 to 10 to the ninth?
Yeah, I wouldn't care at all if you said 2 times 10 to the ninth, 1 times 10 to the ninth, 3 times 10 to the ninth, 4 times 10 to the ninth, 5 times 10 to the ninth, 6 times 10 to the ninth. Once you start getting around 8 or 9, then I'm saying that's 10 to the 10th. So that would be a problem normally, unlike that last one where I showed you that I told you could it be either 10 to the 6th or 10 to the 7th. This one would be a case where no, I would want the 10 to the ninth, not 10 to the 10th or 10 to the 8th. That
Okay.
makes sense.
Yeah.
Okay. Now, just so you'll know, there's, like I told you, there's certain things we should know, like the number of people on planet Earth, the number of people in the United States, that kind of stuff. There's also a nice, quick approximation that you should know for the number of seconds in a year. So I'm going to treat this as if it's another example, but in reality, all I'm doing is trying to get you guys to do a quick calculation so you'll know a nice little result that we can use. So, example about how many seconds are in a year. Okay. Now, I will tell you the approximation we use. The approximation we use is pi times 10 to the seventh. That's really good. It's almost good enough to be correct to three sig figs, but it's good enough to be correct to two sig figs, definitely. So let me show you by calculating it, and you'll see that I get 3.15 instead of 3.14. So that's literally the difference. But 3.15 times 10 to the seventh is the number of seconds in a year to three sig figs, but the two sig figs, pi times 10 to the seventh is enough. So let me show you. 1 year is equal to 1 year is equal to 365.25 days, and 1 day is equal to 24 hours, and 1 hour is equal to 3,600 seconds. So you can see I'm not taking the time to cross out all those units this time. I'm just trying to rapidly do the calculation. And when we do this, what we get is 365.25 times 24 times 3,600. And with that, you get 3.156 times 10 to the seventh seconds. So you can see it's sort of 3.15. Technically, we should round it to 3.16, but it's really close to at two sig figs, it's right on the money. At three sig figs, it's off by 2 digits in the last digit. But that's basically it. We can say 1 year is approximately pi times 10 to the seventh seconds. Okay, so that kind of stuff just comes in handy. Sort of like later on we'll learn in the ideal gas law that a ideal gas at standard temperature and pressure takes up 1 mole of it will take up 22.48 liters, and that's a figure that we can use over and over again. For instance, to estimate the weight of air in the room, stuff like that. You can also find that people will have you try to memorize the energy that electrons have at a temperature of 20 degrees Celsius, all sorts of stuff like that. So this is just another example that can help you doing other calculations. Now, a really cool one here is example 1.9 that I'm getting ready to do. And this example is one that you guys can do as an extra credit if you'd like. I actually allow my students to do it as a extra credit where I give them extra credit as if they did a whole nother lab. Now, you guys are my NO2B class, so you have another lab instructor instead of me. So I can't give you the extra credit for the lab, but you can still do it, and I'll give you extra credit. I'll probably count it as two extra credit homework assignments. But if you go somewhere and find a lake or a body of water where you can actually do this, it'll need to be a distance of at least around 5 miles across. And you'll need to be able to measure that distance, which you can use Google Earth to do. And you'll need to be able to use a ladder or stand on a truck or something to measure exactly how high you have to be above the water level to see the water level on the other side of the body of water. But I'm going to explain it with this example, which is example 1.9. So let's see. Example 1.9 says, believe it or not, you can estimate the radius of the Earth without having to go into space. See the photograph on chapter 1. If you have ever been on the shore of a large lake, you may have noticed that you cannot see the beaches, piers, or rocks at water level across the lake on the opposite shore. The lake seems to have bulged up between you and the opposite shore, a good clue the Earth is round, despite what, X will tell you. The lake seems to, or I already said that part. Suppose you climb a step ladder and discover that when your eyes are 10 feet, 3.0 meters above the water, you can just see the rocks at water level on the opposite shore. From a map, you estimate the distance to the opposite shore is 6.1 kilometers. With h equal 3.0 meters, estimate the radius of the Earth. So this is a really neat thing. I had a student do it last semester using a spot on the ocean front in Virginia Beach and another spot. I think he was looking at the eastern shore, and he could just do it it that way, and that works really great. And you can use Google Earth because when you use Google Earth, it'll actually show a dot exactly where you are. And then if you can find something, some structure that you can look at to know exactly what part you're looking at, you can stretch out a line across that in Google Earth, and it'll tell you how far that distance is. It'll tell you in meters, kilometers, miles, whatever you want. Again, you should always try to do these calculations in meters, kilometers, stuff of that sort. But let me show you how we're going to go about doing this. So I'm going to draw a not scale model of the Earth because I need it to be not to scale, or else we wouldn't be able to see the details. So I really want it to be able to see the details, so I have to show it as it is. So now I'm going to take and imagine that the Earth is a sphere, which it obviously is, right? And I'm imagining this purple line is a radial line that comes from the center of the Earth to the distance on the far edge of the body of water that we're looking at. Now, there's another radial line that goes from the center of the Earth to the other part of the lake, or to the other end of the lake, and I didn't do very good on this, so I'm going to fix it a little bit better. I'm going to try to draw this more circular so that that looks more compelling as a sphere. So this part right here is also R. And what we're saying is that this is some body of water. Now, what the problem tells us is that the distance they call D is equal to 6.1 kilometers, and the height they call H is equal to 3.0 meters. So what we're going to do now is imagine a tangent line at the far side of the lake, at the top of the sphere, tangent line, and that tangent line would be basically perfectly horizontal, and therefore it's perpendicular to the R line that we drew. And then if that's the case, then what we have set up here is like a little ladder with a platform, say, and a person standing on it. And the person has decided that they can see it when the height is, as we said, that height is H. Okay. So, because the line of sight is a tangent line at the opposite edge of the body of water, that means this is a right triangle, and there's your right angle. So the Pythagorean theorem would tell us that r squared plus, now here's the part that the fact that I made this not to scale makes really confusing, but if you drew this to scale, that triangle would be like infinitesimally narrow. It would be really, really, really narrow. And when you draw it really, really, really narrow like that, you would make a case that this red line is approximately equal to the distance across the pond. Notice it looks entirely different because of the scale, because the scale suggests that this is the distance, and that's clearly somewhat different than this distance. But if you had drawn it really more to scale, it would be something like this. Oops. And my program can't even handle that, but it would be something like this. And that would be the angle, and the lake would be right here, and that right angle you can see is much more consistent with being the distance across the lake. So that's what we're doing here. So according to the Pythagorean theorem, r squared plus d squared is equal to the hypotenuse squared, but the hypotenuse is r plus h. So it's r plus h squared. Well, That's easy enough. We can say r squared plus d squared is equal to r squared plus 2rh plus h squared. Remember the binomial theorem and the lesser sense of basically whenever you square a binomial, you take the square of the first term and then you take 2 times the product of the two terms and then you take the square of the last term and you add them all up. That's what happens when you square a binomial. That's what I just used there. And now we can see that the r squared on both sides cancel out, and I can go ahead and solve for r as follows. I'm going to take and pull the d square or the h squared over to the left, so I have d squared minus h squared is equal to 2rh, and I'm solving for r, so I'll divide both sides by 2h, and therefore I get r, the radius of the Earth, should be equal to d squared minus h squared over 2h. The d, as we said, and here's the key point. Just like before, when I divide things and stuff like that, I got to pay close attention to the units. So in this case, I got to make sure I have the same units for all the measurements. And what I'm going to do is use instead of using, the height as kilometers, which would be a really small number, I'm going to use everything in meters. So the D in meters is 6,100. And the H in meters, of course, is 3.0 meters squared. And 6,100 minus 9 is essentially 6,100, or I should say 6,100 meters squared minus 9 meters squared is essentially 6,100 meters squared. So you might not even do that little 3 meter part, but you definitely have to have it on the bottom. So when I take and square 6,100, I get 3.72 times 10 to the seventh, and then I subtract from that 9, I get 3.72 times 10 to the seventh, just like I said. So this is 3.72 times 10 to the seventh meters squared divided by 6 meters because 2 times 3 is 6. So if I divide this 3.72 times 10 to the seventh by 6, I get the radius of the Earth is 6.2 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 meters, which is 6.2 times 10 to the third kilometers. So that's our estimate of the radius of the Earth. And to give you some perspective, the actual radius of the Earth, and in astronomy, the symbol for the Earth is a circle with a plus sign in it, is 6.378 times 10 to the third kilometers. So you can see I'm on the order of a couple percent error. So this is a really good approximation. Anybody have any questions on that? All right, so that's a neat little one. And like I said, if you guys want to, you can do this lab and then turn it in. What I would need is you writing a little, roughly about a page describing everything you did, what the measurements you got, photos of the Google Earth that you used, showing exactly where you went and exactly what you were looking at and that sort of thing, and then show me, of course, the calculation. And like I said, that'll be a really nice extra credit if you want to do it. Anybody have any questions on that? All right. So I talked about Rico Fermi and that sort of thing. We are now completely finished with chapter one, and of course, you have homework this Sunday, or actually, since you guys meet on Tuesdays and Thursdays, all your assignments will be assumed to be due on Monday at 11:59 p.m. So every Monday at 11, I mean, you should expect every Monday, you should expect that there's going to be at least one or two assignments due at 11:59 p.m. on Monday. So keep that in mind. This is very important because I don't want you to miss deadlines. And not only that, what I'm thinking about doing is even though chapter one is going to be due this weekend, then that would mean probably chapter two and chapter three would be due next weekend. What I'm leaning towards doing is making it due a week thereafter. But by doing that, I free up your ability to not worry about, making sure you get all the homeworks done at exactly the right time and everything. So I give you a little bit more of an extension, but the downside is there's going to be some times where you'll have a chapter test that'll cover chapters one through six, say, and your homework for chapter six won't be due until after that test is due. I don't normally like doing that, but I don't mind doing it as long as you guys realize that, hey, the whole purpose of doing the homework is so that you can learn how to solve physics problems. So as soon as I start doing a particular chapter, you need to immediately start doing the homeworks from those, at least starting off with the problems that are called tutorials, because those are ones that are meant specifically just to teach you how to solve the physics problems. So that would give you enough time to do some of the tutorials, and you can go ahead and start on taking the practice test immediately. And as you run into problems on different types of problems in the practice test, you can go back to the homework and look for similar problems and try to make sense of it, and then go back and work on the practice test some more. And that would give you, by me pushing the homework dates a little bit back, that would give you more time to explore a little bit. So be advised, I may actually be doing that where the homeworks might be due occasionally after the tests are due. But if you're going into a test without having tried any of the homework, there's a high probability that you're going to fail, and I don't want to do that. But it's nicer because, like I said, I give you more time on homework. So that's what I'm leaning towards. I just want to keep you guys in mind, to keep that in mind. And I also want you to remember that every Monday, you should expect two or more assignments to be due at 11:59 p.m. So make sure you have them done every time. Not only that, you're also going to have online tests that are due about every two chapters. You're going to have practice tests that are due at the times of those online tests, and you're going to have practice tests that are due at the times of those face-to-face tests, and all of that stuff has to be due on time too. So keep that in mind. Anybody have any questions on anything from chapter one or syllabus information or anything like that? Maybe you've tried some homeworks or some practice test problems and you didn't understand them and you'd like to get me to help you with them. Any of that? And you can type them too, because I am paying attention to the chat window. Okay. It looks like you do not have any problems. Or any questions. So I'm going to go ahead on, but I want to first stop sharing my screen here and I want to start sharing my screen with my Canvas page on it because I want to talk to you about some stuff. Uh, when me, the old person that I am, was majoring in physics and going to college, we didn't have access to the internet. I mean, the internet was just coming out. I remember getting my first email account when I was an undergraduate at East Carolina. I didn't even have one when I did my first 2 years at the community college I went to, College of the Albemarle. They didn't have email back then, at least not there. So I did have it when I got to East Carolina and then later at Chapel Hill as well. And then not only that, while I was at East Carolina, I got introduced to the internet and started using stuff there. But in general, the internet wasn't that useful. There wasn't a lot of stuff. It was actually very useful, I should say, but it was very useful in the tech sense. Like I subscribed to a lot of, can't even remember what they were called, but basically there were these forums and it might have been called forums, but there were these forums which you could subscribe to via text, and people would just type stuff about, niche items. Like I was on one where we talked about Star Wars. There was another where we talked about Star Trek. I was on some where we talked about particle physics, some where I talked about relativity, all sorts of stuff like that. but we just didn't have access to all the stuff that you have access to now. So when we were trying to figure out how to solve physics problems, all we could do was use the textbook and maybe some books that we'd find in the library. So I want to explain that to you because that's still a very valuable skill that you should know about and a very valuable resource that you should know about. So what I'm going to do is share my Canvas screen, and what we're looking at right now is this is the problem set for chapter one. If you just look under problems, and what you'll see is notice this is section 1.3, measurement, uncertainty, and significant figures. All these problems right here are all problems related to section 1.3. Now, in addition to that, these numbers 1, 1, 1, the I's, in other words, they suggest that they're a little bit easier level problems. The twos are a little bit harder. If you read the intro in the front of the cover of your book, you'll learn exactly what these 1, 2s, and 3s mean. And that's important to know. But the point I'm trying to make here is you can also find in the back of the book that the answer for number 1, and you'll find the answer for number 3, and you'll find the answer for number 5, number 7, number 9, and number 11, and number 13. So what we had to do was when we had a problem we were trying to solve from the book or from something the textbook, the author made up or the teacher made up for us, we would try to find a similar problem in the homework set at the end of the chapter, and specifically we'd try to find an odd one. So we'd say, oh, well, this looks sort of like the problem I'm doing, number 7, and that's odd. So I'll go ahead and solve number 7, and then I can quickly go to this where you'll see at the end of the book are, where's it at? Where's it at? Where's it at? Answers to odd number problems. So I can click there, and then I can click here, and I'll see for chapter one, here's the answer for problem one, here's the answer for problem three, and here's my answer for number 7. Okay, that is a wonderful resource. You have that for every odd problem in the end of the chapter. And not only that, there's a ton of end of chapter problems. I just showed you the ones for section 1.3, but notice right here it says problems and then it says general problems. These problems are all oriented with respect to what subsections they're related to, and this one's just generic. So you don't know what section it's coming from, and you got to know exactly, or you've got to be able to solve it with your whole knowledge of chapter one, not just from a single section. But when I click over here, I can look and see, okay, all these problems are there. Then I've got sections 1.4 and 1.5. I've got all these problems, and all the odds have answers. Then I'm up to section 1.6, and again, all the odds have answers, and so on and so forth. So these are wonderful, wonderful resources that you had. About my third year in college, one of my professors, Dr. Sikora, came to me, and I had asked him a question about mechanics, which is a pretty tough junior, senior level class. And I explained my problem, and he was able to help me a little bit, but he said, you know what you really need is a Shaw's outline, and I hadn't heard of such a thing. So he came by about an hour later. He went down to his office and got a copy of what's called a Shaw's outline. I want to type that because y'all might have not heard of that before. So this is something that also exists, and it's printed. It's book published by McGraw-Hill. They're called SCHAUM S apostrophe S, Shaw's outlines. There's one called Physics for Scientists and Engineers. There's one called University Physics. There's one called College Physics. And not only that, they extend into chemistry, programming languages, philosophy, mathematics. There's a ton of them in mathematics. And I have, well, just looking up above my desk, I see 8 of them. And for instance, here's one on differential geometry. Okay. And then if you look at the back, it's got all the different titles of all the different courses you can get for these Shaw's outlines. So that's another wonderful resource that you can use. And if you look through it, what it has is essentially it sort of has a chapter that's reminiscent of each chapter from the equivalent differential geometry textbook, and it has its basically shrunk down to maybe a page, page and a half, and it's nothing but sort of here's the principles that you need to know, and then all the derivations and stuff that are normally done in textbooks, it does those in the problems as if they're problems they're asking you to do, and then it gives you a complete solution, not just an answer, a solution. And then it has a ton of other problems that they ask you and you can try to solve them, but they give you the solutions. And then it gives you on the order of maybe 50 to another 100 questions from that same chapter that they just give you the answers to. So those Shams outlines, which you can find for this course as well, have a copious amount of solved problems. So you can look at solutions to see how they're done, and you can look at solving them yourself and just compare the answers. So that's another great resource that I want you guys to know about. Uh, Now that I've done that, I'm going to go to chapter two and start talking a little bit about that. Chapter two is describing motion, kinematics in one dimension. And you can see the sections are 2-1, reference frames and displacement. And the relevant information that I normally tell my students about that is I talk about Buckminster Fuller, who you might know from the Buckyball. But anyways, he said we are on spaceship Earth. And what he's trying to communicate a little bit there is that there's no real such thing as a rest frame. There's no such thing as a coordinate system or a frame of reference in which it's not moving. Because you think for a second, the Earth, I look at it, it doesn't feel like we're moving. I can't, like when you take off in a very fast car, you can feel your stomach lose a little bit of energy and you can feel yourself pressed back in the seat, stuff like that. Or you can go over a railroad track and get butterflies in your stomach. I don't feel any of that stuff while I'm sitting on the Earth. So we generally think of the Earth as if it's not moving. But it turns out the Earth is moving literally thousands of meters every second, tens of thousands of meters every second as a result of it orbiting around the sun. Not only that, as a result of it rotating on its axis, it's going on the order of thousands of meters per second at the equator, and it's gradually less as you get higher and higher or latitudes to the north or higher and higher latitudes to the south. So if you combine those speeds, you're really talking tens of thousands of meters per second as a result of the orbiting around the sun and the rotation of the Earth around its axis. Then, in addition to that, our solar system is orbiting around our galaxy on the order of 50,000 meters per second. I think that's the figure. It's been a while since I taught this, so I might actually be slightly misremembering numbers, but the numbers are really big and huge, and that's the important point, is that there is nothing that's sort of sitting still. And then our galaxy is actually barreling towards the Andromeda galaxy around 100 million or excuse me, 100,000 meters every second or somewhere around there. So in reality, there really is nothing sitting still. And that's what Buckminster Fuller was doing when he was talking about spaceship Earth. So when you go to set up a coordinate system to measure motion in this chapter, you're going to have to always keep in mind that, hey, I've got to say, this is my coordinate system and I'm tying it to planet Earth. And there's some probability that since the Earth is rotating on its axis and since the Earth is orbiting around a sun and since the solar system, which this part you hardly ever have to take into account, but since the solar system is orbiting around the galaxy and the galaxy's barreling towards another galaxy, that I might ultimately figure out that this reference frame is not an inertial reference frame, which we'll learn about in chapter 4. Okay, so that's part of what we're learning about reference frames. But another thing that's kind of common, and this allows me to talk a little bit about the history of physics and where we are now in physics, is that Carl Sagan said we're all star stuff. And he's right on the money on that. And you might have heard Neil deGrasse Tyson say it a couple times as well. But what he means by that, I suspect most people don't know. And unless you get to major in physics or get to take one of our astronomy courses, you will never get to do it. So the only place you'd learn it in this textbook is maybe in the cosmology chapter, which we very rarely get to. So I wanted to give you a little idea of what that was. When we say we are star stuff, I can tell you what we're basing that on is the following. So, as best we can tell, the universe was created in what has been called a Big Bang. It's a bit of a misnomer because it was neither big nor did it make any sound because space is mostly a vacuum and sound can't travel through a vacuum, so it can't be loud at all. So it's definitely not a bang. And in fact, at one point around say 13.3, 13.5 billion with a B years ago, the entire universe could fit inside of the nucleus of an atom. It would even be way smaller than that. So it's not big either, right? But that's as best we can tell. That is the origins of our universe, and we didn't predict that that was going to be the case because we wanted it to be. That idea was thrust upon us because there was no other explanation for the observations that we've seen. For instance, what happened was we had a model or an idea of the universe that was given to us by Aristotle and the ancient Greeks, and that was called the Aristotelian model. And basically, the ancient Greeks had the thought that we might actually be orbiting the sun. We might be in rotation or in revolution around the sun. But if that was the case, then they'd expect that when the sun is here and the earth is here, we would have one view of the stars, but when the sun is here and the earth is here, we would have a slightly different view of the stars. Sort of like this, if we consider the earth being at one side of the orbit as our right eye and the earth being at the other source of our end of our orbit being the left eye, and this being a different star, then what happens is I see that when I'm in my left eye, I see the star, which is supposed to be a distance away. I actually see it with my left eye up against the right side of my computer screen. But when I'm over here on the other side in my right eye, now I see it in the middle of the computer screen. That's called parallax. So if we're actually moving from one side of the orbit to the other, there should be some stars that we'll see moving back and forth compared to farther back stars. And when they looked to see that, they couldn't see it. So they made the conclusion that either the universe is so big and stars are so far away, we can't detect that motion, or two, we're not moving. Well, they just couldn't imagine that the universe could be so big that they couldn't measure that parallax. So they went with the less awful design idea, and that was that we were the center. So that's how we came down to a geocentric model of the universe that was called the Aristotelian model for a long period of time, even though it was started before Aristotle. It was cleaned up by Aristotle, but then it was cleaned up by several people thereafter and looked quite a bit different by the time we get to the Copernican revolution. So, uh, we were thrust into the idea of the geocentric model because of that. We have since discovered that that parallax is, in fact, there and we can see it and it's pretty significant. Okay. But we didn't know that at the time. But that being said, we had Aristotle, who was sort of the first in recorded history of the big brains of the universe. And he was a brilliant logician, and he had worked out a lot of logic and argumentation and discussion and stuff like that. And he had reduced the laws of nature down to certain premises. And premises were, in some sense, what he thought was so obvious that there's no sense in proving it. So, and a lot of them were obvious, but some of them turn out to be really quite quaint and stupid in retrospect. So, for instance, Aristotle suggested that the universe was made up of four elements: earth, wind, fire, and water. And then there was the fifth element, which was the quintessence, or the heavens. And of course, there's a joke on that where Mila Jovovich played the fifth element opposite Bruce Willis in a sci-fi movie. But anyways, I only think maybe 12 people saw that. But anyways, that's what the science of Aristotle came up with. And it was more than just saying there was four elements. What he did was explained all of the motion in nature in terms of those four elements. So things had a natural place, and the natural place that they had was indicative of what they were made of. So things made of earth had their natural place at the center of the earth because, yes, Aristotle, long before Christopher Columbus, was very certain that the earth was a sphere. Aristotle knew that. And in fact, Aristotle had calculated the radius of the earth and got off pretty bad. He was off by like 40%, whereas Eratosthenes had done it way better. And had Christopher Columbus known of Eratosthenes' result and knew that that was correct, he might not have even planned his trip to find a passage to India specifically because the Earth would have been so big without the knowledge of North America, South America, that whole continent. Without the knowledge of that continent, the ocean would have been so big that technologically Christopher Columbus might not have been able to survive as long as a trip as he needed. So luckily, he had Aristotle's data in which the Earth was rendered way too small by his calculations. But either way, it happened that way, and that's where we ended up discovering the New World and that sort of stuff. But that all led to Aristotle's idea of the earth, wind, fire, and water, where if something's made of earth, its natural place is at the center of the earth. If it's made of air, then its natural place is up above the earth, just like the air in our atmosphere. If it's made of fire, fire is like the sun. They thought of the sun as if it were fire, and that fire, of course, has its natural place up over the atmosphere. So when you burn, for instance, a tree log, what you see is the smoke lifting up and some parts falling back down. The stuff that's falling back down are earth components, and they're trying to seek out their natural place, which is the center of the earth. The smoke is partly fire and partly air, so air's place is above the earth's surface. That's why it's floating. And then the fire's place is above the atmosphere, so that's why it's floating even further up. So that was sort of the whole big idea that they had regarding physics. And you'd be surprised how many times you'll find yourself thinking Aristotelian. You'll think of physics in terms of Aristotelian thought. And that's the odd things. But we're teaching you that, and you'll read it later when we get to Galileo and stuff. But basically, Galileo comes along and realizes that there's some problems. Specifically, Galileo did not, I repeat, did not invent the telescope. What he did was, I think you read of Hans Lippershey, I think that was his name. Read of someone creating a spyglass, and then he created his own spyglass. But what he did do was he took that spyglass, made it better, and looked at the stars and the planets and stuff of that sort. And because of that, he was able to make discoveries no one had before. Now, there was a Thomas Harriot that was part of the mission to the Manio, what's now modern day Manio or Roanoke Island. And he also, around the same time of Galileo, turned his telescope towards the moon. And in fact, we have some documents showing that he actually made some observations of the moon before Galileo did. But because he was in the backwoods of America, that publication never came out until long after Galileo had, so he doesn't get credit. But it's kind of interesting to know that. Now, in addition to Aristotle coming up with those laws of physics based on the four elements and the quintessence, he had one premise, which was that the heavens are perfect, and therefore the perfect heavens means that they're immutable. They can't change. So the reason being is if the heavens changed, they would be changing from perfection to imperfection, or they would be changing from imperfection, which they can't be, to perfection. Both of those were intolerable, so he couldn't handle that at all. So he said the heavens must be immutable. So anything that's in space and moving's got to continue moving exactly the way it was, and it's never going to change. Not only that, the perfect shape is the sphere, and the perfect shaped in two dimensions would be the circle. And since the heavens are perfect, everything in the heavens has to be spheres or circles. No no ifs, ands, or buts about it. So what he ended up doing because of all that is he pictured the Earth as the center, and then he pictured all the orbits of all the planets, which Greek word planetos actually just meant wanderer because there was these stars in the sky that always looked the same day in, day out, year in, year out. But every now and then you'd have this bright star looking thing that would wander through a constellation, and that wandering would literally include loops, made them call it wanderers. And in Greek, wanderer is planetos, and hence we have the name planet. But that's what he was trying to figure out is what kind of motion these things had. But in doing so, he had his premise that the heavens are perfect, so he could only allow them to have circular orbits. The Earth could only be circular or spherical. The other orbits had to be sphere. And in fact, what we pictured was there were giant crystalline spheres that was centered on the Earth. And each one of those crystalline spheres sort of contained the planet orbiting the Earth. So we had outside of the Earth a crystalline sphere that in which the moon was embedded, and the moon would ride that crystalline sphere around the Earth. And then outside of that was a crystalline sphere in which the sun was embedded, and the sun would orbit around the Earth as well. And then outside of that was another crystalline sphere where you'd find Mercury. Mercury would have a crystalline sphere where it orbited the Earth as well. And then there was another one for Venus, and then there was another one for Mars, and then there was another one for Jupiter, and then there was another one for Saturn. And that's all they knew of because those were the ones that they could see with the naked eye. Well, as luck would have it, that also happens to be the number of days of the week because that's exactly how we got the number of days of the week. It's obvious, of course, Sunday is based on the sun, and Monday you can probably guess is due to the moon day, and that's exactly what it is. But in fact, it turns out that Tuesday is Tuesday, which is basically one version of a name for one of the Greek gods. Actually, it even goes through the mythology of the Vikings and stuff like that, the Nordic mythology as well. But each of those names that we now call Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Saturday's obvious again, but each of those names can be traced back to names for the planets and the heavenly bodies. So the moon, the sun, and the heavenly bodies. So that's why we have a 7-day week, for instance. Plus, the number seven turned out to be super important to everybody. That's why, for instance, we have Roy G. Biv. When you really can't really specify exactly what the difference is between indigo and violet, Newton was just wanting to make sure that he came up with 7 different colors for the rainbow. So he said it's going to be red, orange, yellow, green, blue, indigo, violet. But anyways, that's basically how science started out with the Aristotelian model. But because these planets looped and stuff like that, you couldn't make any sense of that with the guidelines that Aristotle's logic told us. So what he ended up doing was make circles inside of circles, what we call epicycles and deferents and stuff like that. And that could account for the retrograde loop-de-loop type motion. However, as Galileo discovered, when he turned his telescope to the heavens, he discovered one problem that we used to completely conclude that the Earth was the center. Specifically, they didn't understand the laws of physics too well because they were stuck in the Aristotelian mindset, where we thought that if, for instance, if the Earth was orbiting around the sun and a bird sitting on the on the Earth on a tree limb, if he looks down and sees a worm, if he lifts up off the tree limb to go catch the worm, then the Earth would leave the bird behind and he would be lost forever. So because of that, there was no way we could envision the Earth orbiting around the sun. So we just assumed the Earth must not be moving. But Galileo looked up at Jupiter and found it had 4 what he called the Medicean moons because the Medici family was super wealthy and he wanted to get some money and some sponsorship. So he called them the Medicean moons. We now call them the Galilean moons, Io, Europa, Ganymede, and Callisto, not to be confused with the Callista Flockhart who married Han Solo. But anyways, that that was the four satellites of Jupiter, and he tracked them day in and day out. And what he figured out was those four satellites were following, staying up with Jupiter. Nobody in no models of the universe had Jupiter sitting still. So that was definitive proof that we didn't understand motion very well. And we didn't have to worry about that bird being left behind anymore because here's Jupiter with four satellites that keep up with it, even though we know it's moving. So that was one of Galileo's ideas that the laws of motion needed to be studied. And when he got put in in-house arrest to avoid basically being burnt at the stake, he decided because he was no longer allowed to publish or talk about or teach about or train anybody in the area of what we now call astronomy, he went to using that in-house arrest as a time for him to study motion. So he started studying balls rolling down inclines and drop balls and stuff like that. That was ultimately what showed him that the Copernican model of the sun-centered universe was right. Now, Copernicus had done so, but Copernicus had done so for all the wrong reasons. That's why I talk about the Copernican revolution being a revolution, sort of like if you've ever seen that T-shirt and it has a big picture of a galaxy on it, and it has an arrow pointing to this little insignificant white dot, and it says "You are here." That's a continuance of what I call the Copernican revolution. The Copernican revolution is where Galileo or where Copernicus decided that the Earth was just one of nine rocks orbiting the sun. Actually, he didn't even do nine rocks because we didn't know about Uranus or Pluto or any of those things yet, Neptune either. So it really wasn't even that. But that idea that we're just a planet orbiting the sun and not necessarily the biggest planet, not necessarily the biggest sun, not necessarily the coolest solar system, and the idea that we are just one end of a branch on the tree of life due to the theory of evolution, all of that stuff is making us not the center of the universe. That's what we refer to, or what I refer to when I talk about the Copernican revolution. There's also around that same time what we call the scientific revolution. And I can't include Copernicus in that because Copernicus specifically said, hey, I think we've lost our way from what Aristotle taught us. He was appealing to authority, in other words. So he said, we've lost what Aristotle has taught us by having epicycles and deference. And that's basically a point by which you have to view the other planets such that they look like they're not changing speeds. And that's not the center of the Earth. So it's just crazy, crazy stuff. But Galileo, having looked at the telescope, saw that Venus had all its phases, full phase, quarter phase, new phase, all that stuff. And with the models of the Ptolemaic theory or the Aristotelian model of the universe, none of those models allow for all the phases of Venus. So to him, that was definitive proof that the Copernican model with the sun at the center was absolutely the fact. Now, I will tell you, he actually knew of Tycho Brahe, and Tycho Brahe had an alternative theory. Tycho Brahe, in fact, hired Johannes Kepler specifically because he wanted to work out his theory, and he was not a good enough mathematician to do it. So he learned that Brahe or that Kepler was such a good mathematician, he went ahead and employed him to do the work. But what his model was that the sun orbits the Earth, but then all the planets orbit the sun. So it's a really complicated model, and that's why it was so hard for him to work out. But Galileo knew of that model and just dismissed it for obvious reasons. It's not a pretty model, but he did not let anybody know that he knew of that model. He just said, "Hey, look, this is impossible. We can't have all these phases of Venus with the Aristotelian model. No, you can't have it with the Aristotelian model, but you certainly could have had it with the Brahe model." But he just swept that under the rug. So he wasn't completely intellectually completely honest. But either way, he was locked in house arrest. He discovered what we now call Newton's first law of motion, which was called Galileo's law of inertia, and all sorts of good stuff like that. He also made leaps and bounds on our study of kinematics. He learned, for instance, that an accelerating object goes a distance that's proportional to the square of the time, stuff like that. So that was all really well and good. But ultimately, what he was able to do was show by using his telescope that we had to accept a Copernican model, where or more specifically, a heliocentric model. And he said that based on experimental and observational evidence. So that's why we say Galileo was the one of the parts of the scientific revolution, because he was taking not the words of authority and not the teachings of other people and not just straight logic disconnected from experimentation, but specifically he was using experimentation to do science and to reach conclusions. So that's the one of the beginnings of the scientific revolution, and we can't count, or I can't count Copernicus in it, because Copernicus was doing it specifically to get closer to what Aristotle taught us. Now, Copernicus did come up with a model, and in that model, it was very natural to have the sun dead center, and the thing that took the least amount of time to repeat its motion was Mercury. So Mercury had a natural place as the planet orbiting closest to the sun. And then Venus was the second shortest time. So Venus was second, and then Earth, and then Mars, and then Jupiter, and then Saturn. And that was the Copernican model. But the Copernican model was stuck in the mindset of Aristotle. So all those orbits had to be circles, and they weren't. They were not circles. Ultimately, Galileo or Kepler comes along, is able to take Brahe's data, and Brahe didn't have a telescope, by the way. He was just observing with like a big protractor and being a very good experimentalist. And from that data, Kepler was able to throw out his own model. He was able to throw out Brahe's model. He was able to throw out the Copernican model, and he had to come up with his own model. And his own model said that the planets orbited the sun in elliptical orbits with the sun at one focal point. The planets sped up and slowed down according to the fact that they traced out equal areas in equal times, and the square of the period of the orbit was proportional to the cube of the semi-major axis. That was Kepler's laws that he came up with, and from that we were able to then calculate far in advance where the planets would be. And that was a big thing. That was what people like Kepler and Brahe and Galileo did for money, because the government ran on the pseudoscience of astrology. So it was very important to them, for instance, what constellation is such and such a planet in, and what constellation was the sun in when you were born, and all that stuff. All that stuff was relevant. And in fact, even certain celebrations and certain decisions, like whether to go to war or whether to get married, all those things hinged on what the astrologers told them. So in order to have these astrologers, you had to have these mathematicians like Galileo, like Kepler, like Brahe, like Copernicus, who could calculate where the planets would be at certain times well into the future. And ultimately, we were able to come up with the Keplerian universe. Even though it was purely epistemological, it was all based on observation with no underlying theory. Newton comes along, however, and discovers his three laws of motion, and part of which were stolen. Or I say stolen. Newton did say, "If I have seen further than others, it's only because I stood on the shoulders of giants." So, in that sense, he was being very humble. But in reality, he also said that in the presence of one of his enemies, a guy by the name of Robert Hooke, who had a short man complex. He was probably about 4'9", 4'10", or something like that. So when he says, "If I have seen further than others, it's only because I stood on the shoulders of giants," he's saying, "I stood on the shoulders of giants, not hobbits like you, Mr. Hook." So it was also an insult, but it was a little bit of a humble statement, where he said that basically he knew his Newton's first law of motion: an object in motion tends to stay in that state of motion unless acted upon by a net external force. He knew that that was basically equivalent to Galileo's law of inertia. His third law, which you guys know, is for every action there's an equal but opposite reaction. That I actually found in one of Leonardo da Vinci's private notebooks. He wrote that it's obvious that when an eagle pushes down on the wind with a force of 50 pounds, the wind pushes up on the eagle with a force of 50 pounds. That's clearly, Leonardo da Vinci knowing exactly Newton's third law of motion. Newton's second law of motion, F equals ma, is the one that was completely new, and that's the part that Newton added. But he also discovered Newton's law of gravity, and once he found that, along with his three laws of motion, he was able to definitively show exactly why Kepler's laws were what they were. He could show, for instance, that the planets, if a planet is to have, or if anything is to have a closed orbit, it would have to be an orbit in the shape of what we call a conic section. So it either has to be parabolic, circular, elliptical, or hyperbolic. And Newton was able to prove that. Far as Kepler's second law, that they sweep out equal areas in equal times, Newton was able to prove that using what we now recognize as conservation of angular momentum, and Kepler's third law, that the square of the period is proportional to the cube of the semi-major axis. Newton was able to prove using basically something equivalent to conservation of energy. So we then had an explanation. If you go forward in time a little bit, we observe nature beyond just the planets, and we start studying nebulas, which nebula is basically just a word that means blur, fuzzy, or questionable, something that's just not that clear. It's almost like a cloud. And one of those nebula was the Andromeda Nebula, and Edwin Hubble had a 100-inch telescope at the Palomar Observatory and was able to look at this Andromeda Nebula. And with that big of a telescope, he was able to see that, in fact, it was not a cloud. It was, in fact, a disk of, or an island of stars. And he could see one of those stars was what we call a dang, I forgot the name of it. But anyways, it was a variable star, and I was thinking of Cygnus, but it's not that. It's a Cepheid variable, and a famous astronomer, a female astronomer, and I wish I remembered her name. I can't remember it right now. It would be really nice of me to have that, but I always forget that name. But she had come up with a law that said when you see a Cepheid variable, the Cepheid variable is going to have an intensity or a brightness that goes like this, and if you find out what the period of that brightness oscillation is, you can determine exactly how massive that star is, and then therefore turn out to find out exactly how much radiation that star puts out. So it's basically a way of us discovering how far that star is away. So when he found a Cepheid variable in the Andromeda galaxy, he could use that data to measure how far the Andromeda galaxy was from us. Well, as luck would have it, because that was fairly new, the data that the female had found about the Cepheid variable was correct in principle, but it was, the numbers were just not off that great, or were not that correct. So he ended up getting a calculation that was a little less than reality. So what he discovered was that the Andromeda galaxy is another island of stars, and that there's billions of them. He could see them everywhere. And what he found out is that the islands of stars that were furthest away were moving away from us fastest, and the islands of stars that were closest to us were moving away from us less fast. In fact, if a star was 100 megaparsecs, or excuse me, if a galaxy was 100 megaparsecs away, it might move at 30 kilometers per second away from us. But if that another galaxy was 200 megaparsecs away, it would move at 30 kilometers per second away from us. And if it was 300 megaparsecs away, or three times as far, it would move at 90 kilometers per second. So that law suggested that all those galaxies were all together at some point in time, and that's how the Big Bang was thrust upon us. We had the data saying, hey, each of these galaxies are moving away from us, and they're not really moving. It's not like the galaxies are moving through space, because if they were moving through space, they wouldn't have that principle where if it's twice as far away, it's going twice as fast. If it's three times as far away, it's going three times as fast. The only way we can explain that kind of behavior is by taking raisins and putting it in bread, and then, raw bread, and then allowing the yeast in that bread to expand expand. And what you'd see is as the bread expanded, the nearest raisin would be moving away from you, but the second nearest raisin would be moving away from you twice as fast, and the third nearest raisin would be moving away from you three times as fast. And that was what he had to picture. He pictured not that the galaxies were running from us in space, but that the space itself was expanding. That's how we got the Big Bang. So it wasn't anything we had a choice of. It was something that we couldn't explain any other way. As luck would have it, there were some major big brains, a guy by the name of George Gamow and his grad student, Ralph Alpher, and another grad student as well, whose name escapes me, but Ralph Alpher did quite a bit. Ralph Alpher is the one who calculated exactly what elements would be present. He calculated what compositions, how much elements would be present in the universe at certain years after it. He was the one that predicted the expansion of the universe that Hubble found, and he was the one that predicted the expansion of the universe and what we now recognize as the background radiation. He predicted that later Nobel laureates won the Nobel Prize. Specifically, it's Arno and Penzias won the Nobel Prize for that. He specifically predicted that even before they found it. So he really should have won the Nobel Prize, but he did it as a senior, as a thesis for his PhD under George Gamow. But George Gamow, being the jokester that he was, said, "Hey, I can't imagine having a guy by the name of Ralph Alpher and me being the name, having the name of George Gamow, and not having someone with the name Beta being on the paper." So he asked his friends, Hans Bethe, who many people called Beta. He asked him if he'd put his name on the paper, and he said, "Well, I don't really want to do that. I'm not going to take credit from your students." He said, "No, the student thinks it's funny too. He'll like it." So Beta did it, or Hans Bethe did it, and he ended up making this paper that everybody called the alpha, beta, gamma paper, which is exactly what Gamow wanted. But because they read it as the alpha, beta, gamma paper, they didn't think it was important, so they didn't really read the paper. So as luck would have it, nobody but the most important people to Ralph Alpher actually read that paper. So the Nobel laureate committee didn't even know about it, but he had actually predicted the black body radiation that Arno and Penzias won the Nobel Prize for, and didn't get the Nobel Prize. He just died like in 2018, I think, 2012, something like that. But him and Gamow were fighting this battle to understand the Big Bang, and another guy, George Hoyt, I think his name was Hoyt, he was fighting the other side because he believed, like Einstein, that the universe was exactly the way it is right now, 100 years ago, 100 million years ago, 100 billion years ago, that the universe always existed in exactly the same state it was. He couldn't imagine the universe expanding, all that stuff. So he was fighting it tooth and nail. But he was also able to do a lot of good stuff. And in fact, he's the one that discovered the very fact that Carl Sagan told us we are star stuff. Specifically, he was trying to make up for the fact that if the universe really was expanding, as Hubble showed us, then the density of matter in the universe should get smaller and smaller, but it didn't seem to be. So he tried to make up a way in which the universe could make mass, which, obviously any physicist would be like, that's crazy. We don't want the universe making up mass. I can't even imagine a scenario. Well, he was trying to do that. And what he ultimately figured out was that stars go through a life cycle, and that life cycle generates the elements. So right after the Big Bang, really the vast majority of what you have is hydrogen and helium. You have trace amounts of lithium, you have trace amounts of beryllium, you have trace even, and each of these are successively less, but you have trace amounts of beryllium and trace amounts less of boron, and then maybe a little bit of carbon, but again, even less, fewer amounts of carbon after the Big Bang. So really the Big Bang just left us with hydrogen, helium, lithium, beryllium, boron, and carbon. And the lithium, beryllium, boron, and carbon were in such small quantities you can't make any use of it. But the first generation of stars would have been made more or less basically of hydrogen and helium. And what happened was the inner core of the star, if the star is comparable in size to our sun, there's no circulation mechanism that allows the gases of the star to circulate into the core and then back out. Well, the problem with that is the core is the only place where it's hot enough for nuclear fusion to occur. Specifically, four protons, four hydrogen atoms will run into each other. First, two will run into each other, and one of those protons will spontaneously turn into a neutron. And then sometime later, another proton neutron pair like that will run into that proton neutron pair, and then that will make the alpha particle, which is a helium nucleus made of two protons and two neutrons. All of that's producing positrons, electrons, neutrinos, and energy, and that is how the star actually puts out heat and lives. Well, luckily, Einstein in 1905 wrote like seven papers, five of which could have won him the Nobel Prize, and one of them did. The Brownian, or excuse me, the photoelectric effect won him the Nobel Prize. His other, one of his other papers was special relativity, and then he turned that in, and the next day he said, "Oh, here's an addendum. I discovered this neat little result, E equals mc squared." Well, that E equals mc squared is what allows us to figure out how the sun is living, because at the time, this is the late 1800s, early 1900s, uh, we had basically one estimate about the sun. Lord Kelvin, I forgot what his regular name is, but he was a scientist, and he discovered that basically, hey, I can use my knowledge of science, and I can use my knowledge of the sun and my knowledge of energy to calculate the age of the sun. And he said, well, our best energy source is coal. So he imagined that the sun was made of coal. And he then calculated exactly how much coal it would be, and therefore how long that coal could burn. And what he came up with, if I remember correctly, was roughly the sun could burn for 50,000 years. Well, our book of record at the time, one of the oldest books we had, was the Bible. And if you go into Genesis, it says, Jesus or God created the earth and the universe and all that. And then, like on the seventh day, he rested, but he created Adam and Eve. And then Adam begat such and such at such and such an age. And then that son begat such and such at such an age. And such begat such and such. And you keep on doing that, and you can add up those years until you get to someone that we know actually existed in history, and that happens to be King Nebuchadnezzar. So we know exactly when King Nebuchadnezzar had lived, and that is correlated in the Bible with one of those descendants of Adam, and we can add up the years, and what we figure out is that the Earth and the entire universe, which, in this time does not include other galaxies, it's just our solar system and about 7,000 stars, but according to the Bible, we would suggest that the universe is maybe around 10,000 years old. That's fine, though, because the sun can live 50,000 years. But around the same period of time, we've got Charles Darwin, who, just to give you a perspective from a time standpoint, Charles Darwin was born on the exact same day as Abraham Lincoln was. So during Darwin's time, who was one of the founders of evolution and one of the big proponents of evolution, he was starting to discover that species actually evolved into other species, and it took large amounts of time. And he was reaching the conclusion that, these species would have to evolve over tens of thousands or millions of years. Not only that, the idea of plate tectonics was coming into play, and people were realizing that in order for this to happen, the Earth would have to be hundreds of thousands or even millions of years old. We now know, of course, the Earth is 4.5 billion years old, along with our sun, and the sun's probably going to live 10 billion to 11 billion years, but we didn't know that at the time. But we were left with this plate tectonics and evolution and all these other different branches of science suggesting the universe and our Earth was so much older than the 50,000 years that that Lord Kelvin's estimate allowed. So we needed some way to understand that. Well, in comes Einstein in 1905 and gives us E equals mc squared. And if you calculate the mass of the four protons that went in and calculate the mass of the alpha particle that comes out, you'll find that the mass of the alpha particle is less than the mass of the four protons. If you take once you get rid of the other little particles that come out, if you calculate the difference in mass between those and multiply that by c squared, then you get the amount of energy that comes out each time one of those nuclear fusion reactions occur. From that, you can take the total energy that the sun puts out and figure out how many reactions are occurring every second, and that'll tell you how long we can expect the sun to continue to burn that hydrogen and the helium and how long it'll last. And when we do that calculation, we can get 10 or 11 billion years, even without the ability of the gas to circulate back in and out of the core. The smaller stars, on the order of 20% or even 10% and smaller of the size of our star, those do have a recycling mechanism that allows the gas to go from the outside into the core and back out and stuff like that. So those stars, really low mass stars, live a really long time. We've got some stars that'll live 20 billion years, for instance, so longer than the age of our universe. That's the fact. And all of that came because Einstein's E equals mc squared, and all of a sudden we've got an understanding of how the universe could possibly be 13.5 billion years old and how our planet could be 4.5 billion years old. All of that came from all of this science. And again, like I said, it was thrust upon us by the data. You can even use the calculations, for instance, that Ralph Alpher did, and we can tell, for instance, when we find a star, we can tell what its chemical composition is, and then from that chemical concentration composition, we can tell how old that star is based on what elements are present, because we can tell the rate at which stars die and live again and reborn and stuff like that, and that contributes to the elements, because the way the stars work is they burn hydrogen in the core, and then when that hydrogen burns out, if the star is too small, it just burns out into a white dwarf. But if the star is bigger than that, the gravity crushes the core as it's running out of that fuel, because the radiation pressure can't keep gravity at bay. So gravity squishes the core, turning it hotter. If it goes from the 10 million Kelvin that's required to burn hydrogen and helium and bumps up to 25 million Kelvin, I think that's the number, then carbon can start to be fused, or hydrogen can start to be fused, or excuse me, helium can start to be fused into carbon. So now all of a sudden, when the universe that only had basically hydrogen and helium, we now have a generator of carbon, and actually some other things come out of it too, nitrogen and oxygen, stuff like that. But then when that core starts to run out of helium to fuse in the carbon, it has another chance for the star to die. But if the star is massive enough, it'll squish again and bring it up to another temperature. And there's another type of fusion that can go on that would fuse carbon into nitrogen and oxygen. And then another one that will fuse something else into something else. And what you end up getting after many, many cycles like this is you get the innermost core is fusing into ultimately iron and nothing else, because iron is a dead end for fusion and fission. Nothing can fuse or fizz energetically favorably into iron. So it's a dead end for the star. It's never going to be a star again at that point. But it's building up iron in the core, and it's building up all those other elements in a shell around it. And in fact, the outermost shell of burning is still fusing hydrogen into helium, and then inside of that, the next inner shell is fusing hydrogen into carbon, and the next inner shell is fusing carbon into something else, and the next one is that something else being fused into something else. And it's like a gobstopper. You've got all these different layers, but you've also generated a ton of elements on the periodic table, more or less just about every other element up to iron. And what ultimately happens is there's not enough radiation pressure coming out of the core, because you're running out of fuel and producing iron, and iron's not going to fuse or fizz, so it's not going to be able to hold gravity at bay. Gravity crushes it and causes what we call a supernova explosion. That supernova explosion blows up, and it puts off so much energy that that star is brighter. That one star is brighter than the entire Milky Way or Andromeda galaxy. for on the order of a couple weeks. But that explosion takes all those elements that were created in those various layers and spreads that all over the universe. And that's where we get all the elements beyond hydrogen and helium. In fact, we can't get anything beyond iron and except for the explosions of supernovas. So gold that you have for your jewelry, which is rare and expensive, that's part of the reason it's rare and expensive because it's only created in the deaths of stars via supernova explosions. Silver's another one. Mercury, I think Mercury was one of them, if I remember correctly. But all these different elements come from these explosions. And not only that, the explosion has so much energy that we've shown in nuclear physics laboratories that all the other elements that we skipped on the way up to iron and all the elements beyond iron that we find naturally occurring, all of those can be generated in that supernova explosion. That supernova explosion, therefore, takes all of the elements of the periodic table and spreads it over some part of space. And that star is normally in a galaxy that's sort of spreading those materials around, running clouds of gas and dust into other clouds of gas and dust, creating new stars that then have not just hydrogen and helium, but hydrogen, helium, carbon, nitrogen, oxygen, the necessary things of life, iron, and all those other elements. And that's the elements that make up our body. For instance, we have to have iron in our blood, we have to have nitrogen, we have to have carbon, we have to have oxygen. All of those are things that came from stars because the Big Bang only gave us hydrogen and helium and trace amounts of lithium, beryllium, boron, and carbon. So that's it. That's a big picture of the entire science as it is today. Uh, of course, I'm skipping a bunch of steps. There's all sorts of cool stories about Einstein, cool stories about Maxwell and Planck and the discovery of quantum mechanics and the invention, if you will, of quantum mechanics by basically Planck writes the first paper, Einstein writes the second paper, then we get Niels Bohr writing more or less the third paper that gives us the Bohr model of the atom. And then from that, we're just on a run where Bohr is sort of directing everything, but he's not doing all the work. He's just sort of the biggest brain in the room that's helping everybody. Einstein's helping, but Einstein doesn't believe in the fundamental ideas that are coming out of quantum mechanics, whereas Einstein created his branch of what we call modern physics, special relativity and general relativity. He did that more or less on his own. I will tell you that special theory of relativity, he got a lot of help from his wife, Mileva Merrick, who he later divorced. And in fact, as a stipulation for his divorce so that he could leave her, he asked that he not be required to pay her any alimony, but that he would give her his Nobel Prize money when he won the Nobel Prize. And he hadn't won the Nobel Prize, but she, being a physicist and knowing how good his work was, and him knowing how good his work was, knew he was going to win a Nobel Prize. So he used that as a bargaining point. It's kind of a neat little story. There's some negative aspects about it that I put in the lecture last night. I'll leave that out today. But basically, Einstein was mostly a humanist and really had a really big, deep heart, but he has certain characteristics of people of that time and didn't always treat people as well as they should be treated. But that's, that's what we face all the time when we look at our founding fathers of America, when we look at Aristotle and Galileo and great scientists. They all had great aspects about them, but they also had very negative aspects about them. And part of it was the times, part of it was just evil, was the way we look at it now. And it's not necessarily evil if, well, it is necessarily. I'll just leave that alone. All right. Anyways, it's 7:40. You guys are free to go. As always, when we ever reach 7:40, you're free to go no matter what. I always wait here till the last person leaves. If anybody has any questions, I can answer it. By all means, if you haven't done so already, chat me your first and last name in the chat box. I'll use that as attendance. I see you made it, Aiden Gallagher. I appreciate you coming. I'm glad you were able to get in. And you guys have a good one. And I will be back on today's Thursday, so I'll be back on Tuesday to see you again. Keep an eye out for my YouTube channel so that you can see if I post any other videos. I recommend you subscribe to it so that if I post a video, you'll get a notification that I posted a video. But other than that, you're free to go, and I'm here for questions until the last of you leave. Thanks for coming, everybody. You're welcome, Ashton.
Hello.
Yes,
Just
Paloma.
just to verify, we don't actually turn in anything on Canvas. It's all done on Pearson My Lab, correct?
Yes, and my Canvas page is what we call deep integrated, so it'll automatically show up in the grade book in Canvas.
Oh, okay. Thank you.
No problem. You're welcome. Thank you, Cameron. You there, Vincent? You've been here longer than anybody. How about Kelton? Do you have a question? All right. Well, it looks like everybody has gone, more or less. Vincent just left. Kelton's still here. Kelton, did you have any questions? Not seeing. Oh, Vincent typed in his name. That's cool. Oh, that was a long time ago. Never mind. All right. Well, I guess that's it. So thanks for coming, everyone. Have a good evening. Thanks again. I'll try to post this tonight, but it might not come up till tomorrow. I hope you have a good one. Goodbye.